Welcome to Ask and Learn.
Okay, so in this problem, you have a sheet or a square piece of metal with some charge, and then you want to get the field super close to it and super far from it. And so to get the field super close to it, you basically want to model this sheet as an infinite sheet. But then if you're super far from it, it's better to model it as a particle because, yeah, that's what it would sort of look like from the perspective of super far and super close. And so I like this one because you can kind of compare like different models, although it wasn't super satisfying because the magnitudes ended up being so different. I think it would have been interesting to compare it for at the same position. But anyway, so to find the electric field for an infinite sheet, that's just sigma over 2 epsilon naught, the magnitude. I'll go ahead and put the magnitude symbol there. And that's charge per unit area divided by 2 epsilon naught. And the charge is, I'll go ahead and write this kind of over here. Oh, I think I'll run out of space if I do that. So the charge is 6 times 10 to the minus 6 coulombs. And then the length of it is 0.08 meters, 8 centimeters. And so when I plugged this into my calculator, I obtained 5.3 times 10 to the 7 Newton per coulomb. Pretty huge field. And then if I evaluate it far away, then I can say that the magnitude of E is the same Q over 4 pi epsilon. Ooh. Epsilon naught divided by r squared. So how far you are from it. And then this r was that was the 30 meters. And then I got 60 newtons per coulomb. I'm just gonna double check this second number and this first number. I'm not sure if I would expect them to be closer, but it does strike me as odd that they're an order of magnitude off from one another. Okay, so for the second one, I still got 60, and then I'm just gonna double check the top one. So because these are pretty quick computations. So 2 times epsilon naught times 0.08 squared. Yeah, I did get a big number there. So I guess in one case you have like a denominator which squares the size versus squaring the distance. The Q and the epsilon naught are basically the same. So I guess it kind of does make sense that you're based on the fact that these length scales are much different, the length of the square versus the distance from the particle. Those are such different length scales, so I can imagine that the electric fields are bigger. At least that's consistent to me mathematically.